here's some material for day 2 of our class. I'm actually only going to cover a couple things, basically so you don't get bored watching this. And I'm also going to do some short videos using interactive figures that you might find helpful for some of the other material that you read about in day 2. So this PowerPoint is only going to cover a very little bit of material that you might find helpful. When you go out at night or during the day, if you really think about it, the sky looks like a bowl that sits on the flat earth. You know, when you look out in the horizon, the blue sky comes down to reach the land, and if you turn around, it looks like that in all the directions. You can't really tell in the sky what things are further away from you. You don't really have a lot of depth perception. So I want to talk about this as a model, because we talk about models a lot in astronomy. And a model is a way of thinking of things that helps you explain some other phenomena. It doesn't mean that that's the way it actually is. We know the sky isn't a bowl. But if we think about it as a bowl, it can kind of be helpful to us when we're describing different things we see in the sky. In this picture, you see a person standing on land, and you see her horizon line, and then you see the sky represented by a bowl sitting upside down on top of her. There's just a couple different points on here that you might want to be familiar with. The point directly above her is called the zenith point. There's a line, an imaginary line across the sky that goes from north to south, and that's called the meridian. Notice our directions are defined on the horizon. Sometimes we don't really think about that. So if you want to face north, she would want to be facing in this direction. Another thing that we use in astronomy is we use the word altitude in a different way. We're used to talking about the altitude of a plane. But for us in astronomy, the altitude is the angle that something in the sky makes with the horizon. So here you see that the sun in this picture is at an altitude of 60 degrees. So anyway, we're going to extend this idea of the bowl to an entire sphere that surrounds the Earth. And this is another model that we use in astronomy. And it's called the celestial sphere. And this comes back from ancient times when people actually believed that the Earth was enclosed by this crystalline sphere, and all the stars were embedded within it. Again, it comes from the fact that when you look into the sky, you don't really have any depth perception. You might sense that a star is further away from you than you think, than maybe another star next to it, but that also might be a trick played because the star is a little dimmer. It actually might be closer. So in any case, we're going to use this celestial sphere as a model to help us understand what we are looking at in the sky. And it actually comes in quite handy. Again, it's a way of thinking of things. It might not actually be accurate, but it helps us understand what we're observing. There's some points that are important in the celestial sphere. If we extend Earth's north pole up to the celestial sphere, we call that the north celestial pole. There's a star that's really close to this that's rather important, and we call that star Polaris. If we go down from the south pole, that's the south celestial pole. And then if we extend the Earth's equator out onto the celestial sphere, we call that the celestial equator. That would be an imaginary line that crosses the sky, but it actually does come in handy in some instances. The other thing that I wanted to talk a little bit about in this chapter is angular measurements in the sky. So think about this. When you look up in the sky and you want to say, you know, how far is the sun from the moon right now, because sometimes the moon is out while the sun's out. Or what if I want to ask how far apart are those two stars? We're used to answering those questions about how far apart with the distance, but think about this. If you took out a ruler and measured the distance between two stars, your measurement would probably be different than your friend's, depending on how you end up holding your ruler. Do you hold it really close to your eyes, or do you hold it at arm's length? Are your arms longer or shorter than your friend's? It's not a reliable way to measure things. Instead, when we're talking about distances or sizes in the sky, we measure the angle. So we measure the angle from one object to the other, or from one side of an object to another. Here you see a picture of how we would measure the angular size of the moon, which turns out to be about 1/2 degree. This picture is showing how we might measure the angular separation between two stars. Here, the angular separation between these two stars in the Big Dipper is 5 degrees. There are a couple different things that determine the angular size or the angular separation of something. The things that determine it are the actual size of the object and the distance. That should make sense to you, and you should be able to know exactly how they might be related, at least in terms of proportional sizes. Think about two things that are the same distance from you, but different physical sizes. Say, maybe a person standing in front of a house. If you back up and you're some distance away from them, which one is going to have the larger angular size? Of course it'll be the house because it's larger. The person who's smaller will have a smaller angular size. Thinking about distance and how that plays a role, we can also determine that. As I back away from the house, it will start to look smaller. So we know that the angular size will be inversely related to the distance, while it was directly related to the physical size. Now, when we look at this picture of the circle, notice that this angle is just a piece of an entire circle. And so using proportions, we can come up with an expression of how we could calculate the angular size, comparing this angular size to the distance and this size of this piece of arc of the circle to the whole way around a circle, or the circumference, which would be related to 360 degrees. If we make a proportionality out of those two things, we can come up with the expression that how we can calculate angular size or angular separation. It is going to be equal to 57.3 times the true size divided by the distance. You might get to use this expression on some of your homework. That's all for this chapter. As I said, I'm going to also make some short videos of some other phenomena in this chapter that you studied, but using some interactive figures that are also available to you through Mastering Astronomy.